multi-party computation. And the lecture recording has now started. So just giving you a heads up for that. Lectures, multi-party, PDF. And then share screen, multi-party. Okay, multi-party computation. So we'll start with an overview and go through a couple of motivating examples. So multi-party computation, or you'll often see it abbreviated as MPC. All it is many actors with secret data that they don't want to share with one another, computing on that data collectively. So to kind of draw a diagram of this, here's maybe person 1, here's person 2, here's person 3, and here's person 4. And all of them secretly have their favorite color. So person 1 is pink, person 3 is pink, and person 4 is pink. And person 2, their favorite color is purple. And what the group wants to do is they want to share what the group's most common favorite color is, right? So what's the mode? What is the favorite color that the most people are familiar with? And this is an example where someone might be embarrassed to share their favorite color, right? It may be a secret, or maybe it's their bank question, right? A lot of those security questions for banks and other systems require you to answer a favorite color type question. So there's actually a lot of reasons you might not want to share your favorite color. And so what we want to do is have a system that allows us to compute on the data, right? Take the mode of the colors, but not everyone wants to share their data. So we need some kind of mechanism for this to happen, for this to occur. And so let's talk about some other examples where you might need this kind of mechanism. So yeah, how can we compute on encrypted data? As another motivating example, right? So if we return to our favorite colors example, let's say we have this data. So we have person A, person B, person C, and all the data is encrypted. But it's can we design a type of encryption that allows us to compute on that data? So let's say they're 1, they're 2, and they're 4. Like, can we design some kind of system that allows us to sum up this data without, revealing that data? So it's like another example of like how you might want to use multi-party computation. Yeah, the classic problem is the Yao millionaire problem, right? How can Alice and Bob figure out who is wealthier without revealing their net worths? Signal. Many of you have probably used Signal. That's the free messaging chat app. And how can Signal, right? Signal has a list of contacts, right? This is all the users of Signal in this list. And then you have your list of contacts on your phone. So how can Signal verify if anyone on your phone is using Signal without compromising security and gaining knowledge of who your phone contacts are, right? So how can you share this knowledge, compute on this data together, but you don't want to give up your data of who's on your phone, and Signal doesn't want to give up their data of who's using Signal? how can two people check if their genome shares any characteristics without revealing any other information about their genome, right? So to kind of draw that example, here is genome A, and here is genome B. And how can we meaningfully compare? How can we meaningfully compare this section of genome A with this section of genome B? And all we want to know is if they share the same genome. But we need a way of doing it that doesn't involve you giving your genome to someone else, because that's not preserving your privacy. Another really popular example is how do we share machine learning data without revealing our underlying data sets? So this is a really interesting one, right? You know, here I am in user land, and here Facebook is in advertising mega giant land. And Facebook wants to take my data, and their goal, right? They want this to happen. They want to give me to give them my data, and then they can compute that against their machine learning models, and they can profile me and do all sorts of other weird things with my data. But what if instead they supplied me with a function, and I could take that function, compute the result, and send it back to them, and then all they learn is the output of this privacy, of this interaction. They don't actually learn the underlying data. I mean, it's still not perfect privacy, but it's better than Facebook having all your data. And this is kind of a lot of web, you know, people talk about Web3 all the time. If you could carry your data between services, then no service would need to maintain and keep your data. And they could only compute on your data with your permission if we did it this way. So this is a really interesting mechanism. So I think that that is just a good kind of primer for some of the motivating examples. Are there any questions on this stuff? I see in the chat a couple of thoughts. So Jared says for Signal, they have codes computed between each party so they can compare. Yeah, they do this thing where you can verify that someone is, that's mostly for verifying between people. But definitely Jared, like they've solved that problem. And for machine learning, so I don't actually know what Facebook does. They don't, you know, they don't want me to know that. They don't want anyone to know that. But they undoubtedly collect the data and compute it on their end. And it would be kind of cool if, you know, you could give them access to your data and you had like kind of a digital identity. Another use case is like governments, right? Like, what if a government, what if like they, you know, what if a government, what if you could give them access to your data for services, but then they didn't have access to your data all the time? There's all kinds of interesting applications for this technology. So multi-party computation. If you want to make a lot of money in cryptography, I think you could build some businesses and applications around multi-party computation. So I'm going to do that poll again, and this is just a sense of how well do you understand the motivations for multi-party computation? Okay. So people are feeling pretty confident in understanding multi-party computation. I don't see any other questions in the chat or I don't see any other hands raised. So we're going to continue on with our discussion of multi-party computation. So we've actually already done some multi-party computation in the homework. Recall from homework 1 the challenge of computing the vote of the class. So let's talk about that. So if you remember, the way it worked was we had a trusted actor, right? Some centralized entity. And then we had person 1, person 2, person 3, and person 4. And person 1, sorry, the central group would send some starting number to person 1, who would then compute vote 1, which was a starting number plus their vote of 0 or 1. And then that would get sent to person 2, who then calculates vote 2. And then that gets sent to person 3, who then computes vote 3, which gets sent to person 4, who computes vote 4, who then takes this back there. And the centralized group calculates the total, which is vote 4 minus C. And if that's greater than 2, then the majority agreed. And if it's less than 2, they could not get more than half to agree. And this particular system had some notable security flaws. So 2 people could collaborate and discover someone else's vote, and someone could lie about their vote. But this is a great example of multi-party computation. So are there any questions on this? Get some of its weaknesses, anything at all? I'll give that 30 seconds. And we'll do another handy poll. So this poll is about how well do you understand this problem and how it relates to multi-party computation. Okay, so we're feeling pretty good about it. If you are feeling like you don't understand this and you're feeling kind of brave, you could message me directly, so privately in Zoom, and I'd be happy to walk through how this works. I think it's important that we all feel comfortable with these ideas. So I'll wait another 45 seconds. And if you can think of what part of this makes you kind of not totally sure, please message me in the chat, either to everyone or to me personally. And then I'll answer your question without revealing who you are. Okay, there were no questions. if you are feeling like you're on the 2 or 3, please feel free to message a question in the chat directly to me. No such thing as a bad question. And yeah, so please, I want to do my best to encourage that. So now we're going to do a few warm-up questions to kind of get ourselves thinking in this multi-party computation way. And notably, what we're thinking about is, can we securely compute exclusive OR? So what do I mean by this? I mean, we have a couple different people, right? We have my drawing tools out. We have person 1 and we have person 2. And person 1 has a bit and their bit is 0, 1. And person 2 has a bit and their bit is 0, 0. And they want to do multi-party computation. So they want to compute exclusive OR together, right? They want to do 0, 1, XOR 0, 0. But they don't want to reveal their data to the other person. Can we invent a protocol that allows them to securely compute this? And the 2 other questions are, can we securely compute OR, and can we securely compute AND? So we're going to take a break till 6:23 p.m., so 10 minutes. And y'all will have that time to think over these 3 questions. And when we get back, we'll discuss those 3 questions and keep moving through our lecture on multi-party computation. Great. So I'll see you all back at 6:23 p.m. All right, it is 6:23 and we are back in class. So what do we think? I'll keep it out for answers in the chat. Uh, do we think we can securely compute exclusive OR? By, by securely compute, we mean, can we compute it in such a way where person one and person two don't learn anything about one another's data? So Jared, you could do it with a mask, but that mask has to be, um, yeah, you could, so if you use a mask, I don't think that affects the answer to the question. Because you can always use exclusive OR to pull the mask out. Yeah, exactly, James. So if you have exclusive OR, right, 0, 1 exclusive OR 0, 0 gives you 0, 1. And there's only one way to get 0, 1 from exclusive OR, and that's to pass it 0, 0 before and 0, 1 before. That's how you would get 0, 1. Anyway, you cannot get exclusive OR. So grab our drawing tool and we'll say, we'll just say no, right? You can't do that. What about OR? Can you compute bitwise OR, right? 0 or 0, 1 or 0. So it has the same problem. If you compute 0, 1 exclusive OR 0, 0, the problem is you still learn something about your neighbor, right? So with a 0, 0, that exclusive OR output is 0. And you both know that the other one has 0. With 1, 0, person 1 doesn't learn anything about person 2, but person 2 learned that person 1 has 0 in this bit position. So we can't do OR. Well, then what about AND? Can we securely compute AND in like this kind of multi-party computational way? Well, not kind of intuitively you can't, right? Because 0, 1, well, that maps to 0, 1 and 0, 0, 0, 0 and 0. False and false is 0. 1 and false is 0. So person 1 and person 2 both learn each other's things. So this is an important property that's relevant for multi-party computation. If the result of the computation can then be contains information about the original values, then you can't do multi-party computation on it, which is kind of interesting. Well, it just isn't perfectly secure. It leaks information, and that's like important to keep in mind as we develop these tools throughout the lecture. So how do we do multi-party computation? How do we actually set this up? If you remember, we use the trapdoor primitive first I'll pause. Are there any questions about this exclusive or and computations? I will pause for 30 seconds again to see if there's any questions. Okay. I'm not seeing any questions in the chat, so we'll keep on rocking. Yeah, so how do we construct these multi-party computations? Well, the building block for it is called oblivious transfer. And it's actually the same building block that, sorry, not the same, but in the same way we used trapdoor functions to construct digital signatures, we can use oblivious transfer to construct multi-party computation. So little oblivious transfer, it's the most simple building block of multi-party computation. And the idea is to establish a protocol where the sender has two messages. They have message 0 and they have message 1. And they send data back and forth with the receiver. And the receiver has two messages, right? The receiver has a bit, and the receiver's bit is 0 and 1. And based on the receiver's bit, they should learn the details of the corresponding message. So if B is 1, they should learn message 1, but they should learn nothing about message 0. Great. Are there any questions on the concept behind oblivious transfer? We'll give that 30 seconds. So to reiterate, the idea is, the sender has two messages. The receiver learns the details of one of those messages, but not the other message. And and this should say the sender doesn't know which one they learned. Let me fix that. Reload that. Let me just close this and reopen. And multi-party. Great. So share screen, multi-party. Great. So just to kind of reiterate that, the sender doesn't know which message the receiver. So how does it prevent the receiver from not learning about the other message? So David, that's gonna be baked into the protocol. That's a great question. So we're going to see in a minute how exactly this works. And we're going to walk through it with some numbers by hand. Yeah, great question. So we're going to review two forms of oblivious transfer, one using random oracles and one not using random oracles. Random oracles, you can think of that phrase as you can kind of almost mentally kind of make a little map, and random oracles, this just corresponds to like hash functions. You'll often see them call random oracles, but they basically are like perfectly random hash functions, kind of. So we have our sender, Alice, and our receiver, Bob. Bob is going to pick a bit, right? Bob picks 0 or Bob picks 1. Then Alice selects two messages, M0 and M1 from the message space. And the messages are just bitwise, 0 to 1 to N. Then Alice picks a random number C from G. Now, G refers to the prime order group. And the prime order group, as you recall from our brief discussion of number theory, is the group that has operations defined over it and goes up until P and then wraps back around. Great. And so then Alice will send this random number to Bob. Bob will then sample their own random secret from ZP. And this secret will call be S sub B. And then Bob is going to compute two values. So if Bob chose, oops, not yellow, I want to do green. So here, right, Bob chooses 0 or 1. So this bit corresponds to this B. So if Bob wants to learn message 0, this becomes H of 0. If Bob wants to learn message 1, it becomes H of 1. And so he either gets G to the SB, or he sets C divided by G to the SB. Then Bob sends H0 and H1 back. So depending, right, if Bob chose 0, then HB is H0, and H1 minus B is H1. So Bob chooses 0, then GSB is H0, and C divided by GSB is H1. If Bob chose bit B to be 1, then B becomes 1, and H1 is SB. And then H of 1 minus 1, or H0, is this value. So that's an important part of notation. It's come up in class before, but I'd love to do a quick poll and see how we're feeling. So how well do you understand this protocol so far? We haven't gotten to the meaty part yet, but how does all of this make sense as what's happening so far? So no hashing yet. What is SB? Great. So, my poll, sorry. I'm going to end the poll. So people were kind of a little confused. So, whoops, close it, stop sharing. So, great questions. Thank you all for asking questions. So, James, to answer your question, Bob's secret, that's SB. Bob is literally just sampling a random number, a random integer that's smaller than P, the prime number. And Aruj, we have not done any hashing yet. William, SB is just this randomly sampled number. So we're not even computing hashes yet. We're going to get to hashes in a minute. But all this is we're taking this number G, let's say G is 9, the generator 9, and we're raising it to SB. And SB is a number. So if Bob randomly picks from a hat 2, then HB becomes 9 squared. And otherwise, right, so that's HB. And then H1 minus B becomes C over 9 squared. So hopefully that helps a little bit. Let's do another poll. Polka. Oops. Yeah. So the B and SB is not related. Yeah. So we can almost, this is just, so the S, so this B, great question. So this B just corresponds to Bob, right? This is like Bob's secret. So it should be like a capital B. Bob's secret. Bob's secret. Okay. I'm gonna realize the poll. You know what? We'll keep going, then I'll do the poll later. Okay. So Bob has got these bits sampled, and he sent H0 and H1 to Alice. Alice first verifies that H0 times H1 equals C, right? So I think it should be somewhat, it should make sense, right? This step, because if Bob, well, we'll get back to it in a minute, but if HB H0 times H1 should correspond to G to the S times C over G to the S. And that should calculate out to C. So that's the first step Alice does. The next step for Alice is she herself samples a random value and computes ciphertext 0. Now, ciphertext 0 is G to the R sub 0. So that's the first part of the ciphertext. The second part of the ciphertext is Alice takes H0, raises H0 to R0, takes that hash value, and applies an exclusive OR to the message. And then Alice does the same thing for message 1. She computes the same thing, samples another random value, computes another hash, and does another exclusive OR. Then she sends these two ciphertexts back to Bob. And then what Bob does, move this out of the way. Bob takes the bit he's interested in, and then he does this. He takes the first part of the ciphertext. So the first part of the ciphertext is this part, G to the R0 or G to the R1. And then he raises that to SB. So that corresponds to G to the RB to the SB. So Bob takes the hash of that value, and then he applies that exclusive OR with the second half of the ciphertext. And the second half is this half, is the same as this. And so what happens is, if we recall that one exclusive OR, two exclusive OR, one, that yields 2. And so basically, you can almost think of this encryption as a one-time pad. And Bob is calculating the key to the one-time pad. And here is a really interesting point. If you skip the step, if you skip this step right here of verifying that H0 times H1 equals C, well then Bob could set H1 minus B to be G to the SB2. And then Bob will be able to unlock both messages. So this requirement is why Bob can't unlock both messages. All right, so let's do maybe 1 minute of questions because this is a pretty meaty slide. And there's a lot going on here. And while you're thinking of questions or just contemplating, I'm going to relaunch the poll on how well you understand this particular proof. The second half of the proof. Okay. I'll just share the results. So people are kind of comfortable but have some questions. Whoops, stop sharing. Okay. So in the second half, Bob has sampled these values and he sent them to Alice. And then what Alice does is first she verifies that Bob came by H0 and H1 honestly by checking that G to the SB times C over G to the SB equals C. Otherwise, Bob could have cheated. So there's pretty unlikely Bob cheated if we can verify this. So now we know Bob isn't cheating. Then Alice generates the ciphertexts. And the way she generates the ciphertexts is she picks a random value and she raises the generator G to that random value. Then she raises H to that random value, hashes it, and applies an exclusive OR to it against M. And then she does the same thing with H1. She does another random value, computes another ciphertext, and sends that back over. Does that help, David? Or do you have another question? Okay. Since there was some confusion, I'm gonna use some numbers here. So does Bob pick 0, 1? Message in the chat. 0. And message 1, sorry, M0 is going to equal 0, 0, 0, 1, 0. Message 1 equals 1, 1, 0, 0. C, someone give me a value for C. Any number between 1 and 13. 5. C equals 5. So Bob has sampled 0. Alice has created her 2 messages and has sampled a random value 5. Then Bob separates another random value. Someone give me a random number between 1 and 13. Great, 8. So then Bob has grabbed 8. Now our prime order group is bounded by 13, which means we can use 7 as a generator. Yeah. So our generator G is 7 and our prime order P is 13 for our group. So 7 to the 8, well, what's 7 to the 8th? That is, oops, sorry about that. 7 to the 8th, 5 million something mod 13 is 3. So let's go to our text. So SB is 8, HP equals, oh, sorry, it's not 13, HP equals 3. delete that. Huh. Sorry about that. HP is 13. C over HP, right? So C is 5. So 5, so H1 minus B equals 5 by 13. Okay. First, verify the H0. So then we send, right, HB and H1 over. Let's verify that H0 times H1 equals C. Okay. H0 is 13 times 5 over 13 equals 5. So we have passed that step. Check off all the steps we've done. Two more steps. Okay. Someone give me a random number R between 0 and 13. 8 or 12. Okay, we'll go with 12. And someone give me another random value for R1. 11. Okay. So we have now sampled R0 and R1. Our ciphertext is G to the RO. So G is 7, RO is 12, and that's all being done mod 13, which gives us 1. So G to the R0 is 1. Oops, undo text. Okay, and same with GR1. So 7 to the 11 mod 13 is 2. So over here, G to the R, G, and this is not like to behave. We'll say G to the R1 equals 2. The hash of H0 to the R0 is 0 H, sorry, the hash of H0 to the R0 equals 1, 0, 1, 1, leading to the second half of that value being, let's see, 1s or that. So we have 1, 0, 0, 1. And then the hash of H1 to the R1 equals 1, 0, 0, 0. That ciphertext becomes 0, 1, 0, 0. Okay. And so that's been computed and that's been computed. So our two ciphertexts are computed. So that brings us to over here. So Bob did message 0. So Bob says, let's take ciphertext B, so ciphertext 0. So Bob says G to the R0 to the SB, which is 8, and R0 is 1. So G is 7, so it's really 7 to the 1 to the 8. Take the hash of that, and that should equal H0 to the R0, which equals 1, 0, 1, 1, and apply 1, 0, 1, 1 exclusive OR with 1, 0, 0, 1, we get 0, 0, 1, 1. So we say M0 equals 0, 1, 1, XOR 1, 0, 0, 1. And that gets us our actual message. So let's do another poll. I just want to get a sense of, do we feel like we understand this a little more clearly now? And any questions, feel free to drop them in the chat as you're answering the poll. What is P at the top? P is the prime order of the group G. So that's the upper, that's kind of the bound of the group. Okay, so we've improved the understanding a little bit. Good to know. All right, so we're gonna keep moving on. James, I answer your question about the prime order P at the top? That was just the, cool, all right. So that was using the hash function of the random oracle to do the transfer of knowledge. Let's see what it looks like when we don't use an oracle. So right, we still sample B to determine which one we're going to encode. Then we sample XY from ZP. And then H equals G to the X, U equals G to the Y. Remember, these little g's are still generators for big G, our group. Then VB equals G to the XY, and V1 minus B equals big G, and the magnitude of the group, divided by XY, divided by G to the XY. Alice at this point samples her 2 messages, and Bob sends over all these parameters. Now, at this point, Alice should also complete that same verification step from before. Right, she needs to verify that V0 times V1 equals G, or the magnitude of the group, just to make sure that's being done honestly. Then she says A0, B0. She samples 2 random values to calculate ciphertext 0 and ciphertext 1. Then these ciphertexts are sent back over as CT0 and CT1. Oops. And then the message is this division. So let's talk about correctness here. How do we know this works? Well, U to the A0, so down here, U to the A0 times G to the B0. Well, what does that correspond to? That corresponds to U to the A0, we'll call it U to the AB times G to the B. And that corresponds to U, which is G to the X to the A, and that is being multiplied by G to the B. And then we come back down. Sorry, this should be H, not G. Sorry about that. This should be G to the Y to the B. Lovely. Okay. And then we look down at MB, so that's CTB1. And then CTP0 is V to the A times H to the B times M, which equals G to the XYA times H, which is H, which corresponds to G to the XB times M. And this is actually, oops, G, that remains G to the B. And so instead of U, right, G, sorry, YA. Yep. So this division gives us M. Sorry, let me just double check this division. I may have misnotated this. So U to the A0 times U to the A times G to the B equals G to the YA times G to the B, which equals G to the YA plus B. And then that's to the XYA plus B. Correct? Oh, perfect. We're sorry about the confusion there. I just mixed up my values there. So, and then this equals G to the XYA plus XB times M. So just to connect all the dots here. So this is CT B is 0, and this is CT B1. Back to purple, and just grab that. Okay, and you'll notice that this is actually CTB0 raised to the X. So we take CTB0 to the X is G to the YA plus B to the X, which equals G to the XYA plus XB. And now, if we take this top value, so let me just do some purple underlining again. So we take the green value and divide it by the purple value. We're left with M, which is our message that was originally encrypted. And only Bob can decrypt it, because this X right here, unless you can solve discrete log, you can't pull that out of H. Okay, I stumbled there for a minute, but are there any questions? I see a yes. Oh, yes is a previous reply. Okay, we're going to do a poll then. There are no questions. I'm curious how well we understand this. So G, David, is the prime order group that all this math is being done under. Group just literally is a group of numbers that certain operations are defined over. And basically, we use the fact that discrete log is really hard to ensure that Bob is only decrypting one of the messages. Does that answer your question, David? Cool. we've got 9 responses and we have 20 people. So maybe there's some good thinking going on. So everyone who's responded seems to understand this well, which is amazing. Okay, the remaining 7, I'm not gonna keep the poll open any longer. So just in case you're curious, people seem to understand this pretty clearly. So that's how you do multi-party. I mean, that's a really cool way of obliviously transferring a message without knowing which message you want to transfer. Um, so that's pretty cool. And there's no random oracles involved. So you can think of some, imagine if, I don't know, there's a lot of ways you can be applying that to do cool things. So annotate, clear slide. So now we're going to move on and talk about Shamir secret sharing. So as a review, oops, it's up there. So to review, we discussed it in the public key encryption lecture. Basically, it allowed us to share a secret with an arbitrary number of people and allow any subset of them to come together and discuss them. So just to kind of retouch that, right, we had our axis and we had a secret right there. And then we had our keys. And if these 3 people got together, they could compute the equation and then understand the y-intercept of this parabola, which then would allow them to come together and unlock the secret. And what was cool is we had, you could have like 4 or 5 people in on the secret, and only 3 of them need to come together to unlock the secret. And that party of 3 can actually reissue the keys if they want to, which is kind of exciting. So I think that's really cool. I got a little excited and put it there in those slides a little bit early, but now we're going to discuss how to actually compute it. So here's the mechanism. So the mechanism uses something called Lagrange interpolation. So if you have your points, right? X0, Y0, X1, X1, Y1, ... Xn, Yn. Then what you can do is the function at X is equal to Y0 times. And at the top, it is X minus X1, X minus X2, ... X minus Xn divided by X0 minus X1, X0 minus X2, and so on and so forth. ... X0 minus Xn. And then that's plus, and it's the same thing, but you shift it all over. So it becomes Y1. Then it's X minus 0 there. And we skip 1. And this becomes 1. And that becomes 0. That becomes 1. That becomes 2. All the way through to the end. Plus, until we get to, same thing until we get to Yn, where it becomes just the end. So x minus x1 is x0 becomes x1 and minus 1. And this is x n minus x0 n minus x1 n minus x n minus 1. And this function, if you plug in like 0, that gives you the y-axis. Now, you only need the order of the function plus one more person. So if it's a parabola, order 2 plus one person equals 3 people. So if you have 5 points and you only need 3, you can pick any 3. Okay. Are there any questions about this? We're about to go through an example of this. But first I want to make sure this mechanism makes sense. And I'm curious in the chat, if you've seen this before, where have you seen this before? You might have seen this in like algebra class back in the day. All right, on that poll. So yeah, most people are saying they understand this pretty well. Seeing a lot of 3s, which I'm taking as understands it like, pretty well. Okay, let's go ahead and clear this off. So we have our 3 points, our 3 shares. Minus 3, 0 is our first point. 2, 5 is our second point, and -1, -4 is our third point. And I buried a secret at the origin. So first we compute f of x, which is 0. So 0 is y1, right? Then it's x minus 2, x minus minus 1, which comes there. Then it goes x1, sorry, x0 minus x1, undo, and so on and so forth. And then we do the same for x1, 5 times that computation, and then -4 times that computation. And so if we continue this on and we plug in 0, why don't you try to calculate that on your own and let me know what you get for the for the y-intercept. Give you 30 seconds for that. Wow. Anyone get it? All right. Well, the answer is actually just -3. So 5 times, let me draw this out. 5 times 0 plus 3, which gives us 3 times 0 plus 1, which is 1, divided by 2 plus 3, which is 5, times 2 plus 1, which is 3. Okay, and then second one is -4 times, then it's 0 plus 3, which is 3. Then 0 minus 2, which is -2, over -1 minus -3, which is 2, times -1 minus 2, which is -3. So then both of those simplify to 1 minus, or 1 plus, then 3 times -2 is -6 over -6. 6 over -6. -6 over -6 is 1. 1 times -4 is -4, which gives you -3. So yeah, kind of cool. Your homework should be to implement this. So should be fun. So I will do a quick poll. How well do you feel like we understand this? Cool. It's a simpler concept, but it's a very elegant way of doing secret sharing. Okay. Computing on secret shared data. So this is the last slide set. So suppose Alice, Bob, and Charlie are friends, and Charlie wants to know how many marbles Alice and Bob have. But Alice and Bob don't want to tell Charlie how many marbles they have individually. So Alice is going to give 2 random numbers to Charlie and Bob, and then Bob's going to give 2 random numbers to Alice and Charlie. Alice then takes her total minus the number she gave to Charlie, minus the number she gave to Bob, and then she adds the number Bob gave her. Bob then computes Bob's original total minus the total he gave Charlie, minus the total he gave Alice, plus the total Alice gave him. And then Charlie computes the total Alice gave him plus the total Bob gave him. And then they all share their results and they independently compute this. So they add their 3 things together in parallel after they share their results. And what does that look like? Well, add minus SAC, and then we have plus SAC. So that and this cancel out. Then we have S minus SAB, and we have plus SAB. Where plus AB go? There it is. Then we have plus SBA. We have minus SBA. Then we have minus SBC. We have plus SBC. And we're left with Alice's total plus Bob's total, which is kind of a cute way of sharing secrets. So this randomness interaction is what allows us to share secrets. So how good do we feel about this? And feel free to drop any questions in the chat about this. Okay. We're feeling pretty good about it. All right. And that is lecture.